Okay, I'm contemplating the following idea, and I'm trying to express it formally. The idea is simply that addition presupposes multiplicity, yet multiplication presupposes addition. So this is an inherently paradoxical idea. What to make of this mathematically? Over here I've written out the 12 basic properties of numbers that Spivak outlines in chapter 1 of his calculus textbook. The point just being to show that up to the point of asserting the existence of a multiplicative identity, 0 is the only number that makes any sense, basically. You cannot prove without the existence of a multiplicative identity that 0 does not equal 1. Once you assert the existence of a multiplicative identity, you can assert that 0 doesn't equal 1, but you can still claim that 0 equals 2 consistently. It's not until you've asserted these final three properties, the trichotomy law, the additive closure, multiplicative closure laws, that you can prove that 0 does not equal 2. That's important for our consideration. So I call this the Presburger paradox, referring to Presburger arithmetic, which is a first-order logic system of arithmetic that does not involve multiplication. That's the point of bringing up that particular system, is to emphasize this logical issue, which is the dependency upon multiplication to prove that, in particular, 0 doesn't equal 1, but as we'll see here, that 0 equals 2 that 0 equals 2 implies that 0 equals 1. So the first axiom of Presburger arithmetic is simply stating that it cannot be the case that 0 is equal to any of its successors. Therefore, 0 does not equal 1, of course. And the system is consistent and complete. However, this assumes in context that were 0 equal to any of its successors, then 0 would equal 1. Namely, it assumes that contradicting this axiom results in logical explosion, or the idea that a contradiction yields the ability to prove any statement whatsoever, basically. However, that's not the case, because it can be proven that for all contradictory statements of the form 0 equals n for n greater than or equal to 2, those statements do not necessarily imply that 0 equals 1, therefore do not imply logical explosion, basically. So the proof of this is very simple. I just say it's a proof by contradiction. Suppose that you could prove this, basically. Suppose that you could prove without multiplication that is a contradictory statement of the form 0 equals 2 or greater implies necessarily that 0 equals 1. I.e., assume you could prove that without the usual proof of that claim in piano arithmetic, which is simply a proof using multiplication, and specifically the multiplicative inverses. If you could do that, then given this model of piano arithmetic, namely given a system allowing multiplication, it could be proven that mod 2 is equivalent to mod 1, meaning it could be proven that binary arithmetic doesn't make any sense. However, of course, by Gödel's dialectic proof and many other proofs of the consistency of piano arithmetic, it cannot be proven, of course, that mod 2 equals mod 1. Therefore, given this model of Presburger arithmetic without multiplication, it must be the case that contradictory statements of the form 0 equals n for n greater than or equal to 2 do not imply 0 equals 1, and therefore do not imply logical explosion. The conclusion is a strange one, which is why I hesitated to write it, but addition is fundamentally paraconsistent, meaning when you isolate addition, as we've done in focusing on the Presburger arithmetic system, you have a system that's provably consistent still. However, you can prove, if you accept it as proof, that contradictory statements, in fact, there are infinitely many contradictory statements allowed in the system that don't result in a logical explosion, which means the system is paraconsistent by definition. So I put a question mark there only because that's a strange conclusion with strange implications that I've yet to fully explore, of course.